All right. Good morning, everyone. Do you hear me well? It's okay? All right. So today we are going together to talk about UAVs, unmanned aerial vehicles, and the interactions that can happen between the electronics parts inside the UAVs and electromagnetic signals. We are also going to consider the several existing neutralization technologies or techniques that exist to assess the threats that the civilian UAVs pose in some specific contexts. This work has been done with my friends Emmanuel Cotet and Shaoqi Kasmi. I'm with the NSSE, which is the Agence Nationale de la Sécurité des Systèmes d'Information. It's the National Cybersecurity Agency of France. And I work with the Wireless Security Lab. Our main focus are concentrated on electromagnetic security, so it concerns the tempests and intentional electromagnetic interferences threats. And we also mainly focus on all the wireless communication protocol security. And that being said, in the agency we are also the reference laboratory for everything that is physical layer. The agenda for today: first I'm going to talk about the context, and then I will briefly remind you the different neutralization techniques that exist against UAVs or civilian UAVs. We will see that we will really focus on civilian UAVs. And also I will try to show the main challenges in designing such neutralization techniques. Then we will talk about the electromagnetic interactions and the directed energy weapons. After that, I will explain how we played with our target in order to create ourselves a framework to study the electromagnetic interactions between our parasitic signal and the hardware parts of the target, and also to analyze the propagation of these phenomena up to the software layer in order to understand how the propagation and what can be the impacts on the target. I will give some results of our test campaign on a specific civilian UAV and some conclusion elements. So the context is that the unmanned aerial vehicles are spreading very fast and are getting cheaper and also more and more efficient. And nowadays, a hobbyist doesn't need to get a pilot license to be able to control and to fly a civilian UAV. And their cost is getting lower and lower, and for that reason also we see that they are more and more used in critical operations by law enforcement agencies, for example, or military forces. What we can see in those screenshots in the bottom of the slide is that in the US the trend is to stop using common off-the-shelf drones for critical operations in the military sector. And in France they consider that in the military field we have to develop specific products, but it might be interesting to acquire and use and operate COTS drones if we need to, because it's cheaper. So they are used in critical operations, and also they can be potentially used for malicious purposes. So this year there have been two main events in France. A drone flew over the holiday house of the president, and a drone was crashed on a nuclear plant by the Greenpeace Association. So there is a need for strategies to assess this threat and to neutralize drones in some specific contexts. And as we are going to see now, there is no perfect answer, and it's really challenging to try to design some technical answers to this problem. And of course, radio frequency directed energy weapons are considered as a possibility for this application, and this will be the main focus of this talk. So I'm gonna introduce the challenges behind drone response and drone neutralization. And in fact, it's a complex process which has 3 steps mainly. The first step is to detect that there is a drone coming. So technically, it's already a big challenge. Then it is necessary to identify the drone in order to use the right neutralization technique according to the drone that has been identified. And often in this process, between those steps, there is also some human introduced delays because of chain of command, for example, or for legal issues. So the response time can be drastically increased because of those issues. For the identification and the detection, the field is not really new. In the military, the techniques and the technologies were already available and somehow expensive. So it's not it's difficult to find the right technology to adapt to some specific contexts. Some techniques use the radio frequency communication links in order to detect that someone is speaking on a specific channel, and this channel we know that it can be used for command and control of the drone, for example. For the identification, some products also rely on the radio frequency communication in order to perform the identification. So sometimes they rely on the MAC address of the drone or of the remote control. And then there are other strategies, radar, using the noise of the drone in order to whether detect its presence or identify the model of the drone. And of course, this is all machine learning assisted. Once you have detected the presence of the UAV, and once you have identified that this is a UAV and this is not a friendly UAV, and you need to find a response, then you have several options. And the first option is try to destruct the UAV. So traditional ballistics techniques can be used, and also directed energy weapons are suggested, and some products already exist in that field. This can pose many problems. The cost of the ballistics versus the cost of the drone, the collateral damage, and in that case the drone will fall, and in some contexts you don't want the drone to fall. Other possibilities is trying to intercept the drone. So in that case, birds can be used in order to catch up the drone while it's flying. This is an interesting technique because they are really accurate. They are somehow self-driven, so you just let the bird go, and it knows that it has to catch the drone, but they can be injured, and it's hard to replace a well-trained bird, and it takes time to train them. So it's an important cost. Net throwing guns also. So these have mainly range limitation, and also the shooter has to be really accurate in order to succeed. And of course, in that case, the drone falls. So again, sometimes you don't accept this risk. And then there are some strategies that have been designed or proposed to use drones to intercept the drone, so that they catch the drone. They replace the bird, in fact. They try to catch the drone, so they have nets or some ropes or cords, and the propellers get stuck in that cord, and then the intercepting drone tries to do something, land and take the threat away. This poses some problems, and the payload weight can be a problem, so some drones are also equipped with parachutes, so that if the total weight exceeds the max limit, they have parachutes to land safely. But again, in that case, the drone pilot, the interceptor drone pilot, has to be very skilled in order to succeed. Some products claim that they allow for taking control of the drone. So in that case, the technique is, the idea is to replace the pilot or disconnect the pilot and then control the drone and flow it away and then land it safely. Usually they rely on weaknesses and software vulnerabilities that are in the radio frequency front ends or stacks, or, and it's mostly the case, on default credentials and misconfigurations of the UAVs. So in most cases, those techniques, if you change the MAC address, it starts to not work so well, and then if you change the default Wi-Fi password, then the solution stops working for the target. And the last possibility is the GPS spoofing. So sending fake GPS signals towards the drone in order to make it think it's in another place and make it land, or and in that case it can pose several collateral damages, because if you do that near an airport you can have problems, I guess. And also on the legal point of view, it cannot be applied in all contexts. And finally, some strategies rely on a special mode. So the aim is to switch the drone into a special mode, into a safety mode. So usually it's based on communication jamming. So you jam the link between the remote controller and the drone, and you hope that its default behavior will be friendly. So sometimes it lands, it's an emergency landing, and sometimes it goes back home to the starting point of the flight. And you can also obtain on some models the same effect with the GPS jamming. But again, the GPS signals are really sensitive, so it's legally difficult to justify the use of GPS jammers. And also, the jamming of the radio frequency communication also poses problems, interference problems with on the ISM band, and you have to take the context and the geographical context into account. So we know that there are several strategies to assess the neutralization problems of civilian UAVs, and directed energy weapons are also considered. So now I am going to briefly remind what directed energy weapons are and how we perform susceptibility testing on equipments in order to identify the vulnerability threshold and then design specific sources or signals in order to exploit those vulnerabilities. Since the 90s, during nuclear tests and shots in a high altitude atmosphere, it was noticed that during the tests, the electronics devices were disturbed in a pretty huge range around the test area. So this started an interesting field, which is the study of the effects of electromagnetic interferences on electronic systems. This analysis is highly required in order to first design appropriate protections for critical infrastructures, and also just to understand how the failure occurs, how what are the physical phenomena, the underlying physical phenomena, and how this spreads through the system until having an impact on the software side. So basically the main challenge is to assess the whole chain here, from the source, which will consist in usually a radio frequency radiating source with a specifically tailored signal in order to trigger the effects, the desired effect on the target. Then the signal propagates from the source to the target, so it can be changed by the propagation path elements. And then there is the energy transfer somehow, and the actual effects on the target. And detecting and identifying effects on the target is really not trivial, because when you don't really see that something is happening, it doesn't really mean that nothing is happening. So this is an observation problem. And of course, when you identify the effect, you can estimate the impact on the functionality of the device. So, back to UAVs. It's important to perform this electromagnetic susceptibility assessment in order to first determine efficient neutralization strategies, or at least to have an idea if it's an interesting strategy, if it's viable, if it can be effective, and if it can be used for several models, for any model, for any drone model, and also for proposing hardening strategies and solutions. There has been previous work on that topic, so people worked on the analysis of the impact of electromagnetic interference on UAVs. But they mainly focused their research on the presence of the radio frequency front end. So their interest was to analyze the disturbance on the radio frequency communication links, for example, or to analyze the impact of having a radio frequency antenna near the electronics of the other parts of the drone, and to see if it causes disruptions on board. And finally, then there has been some research also on the interactions between other radio frequency systems, mainly cellular networks, so base stations, and their impact on the functional safety of the drone. The most interesting effects, I guess, were observing some motors malfunction, and mainly people working in that field usually put the target in a test facility, and then they put also video cameras, and they go out, they shoot, and they observe literally the effects. So if the drone falls, there is an effect. If it doesn't fall, there is no effect. And this is a blurry way to observe the effects. And we proposed an approach which brings the observation point on the system, on the target system. So our proposal is to try to run software on the target and choose some observables in order to gather information on the system state and try to understand which parts are impacted by the parasitic signal, for example. And so this poses two main questions. The first is how to choose what to observe. And the second one is how to do it on a closed system. So we have to run our own software on the system, and sometimes it's not so easy. And this brings the question that was raised by Halvor Flake in his keynote in STIC 2018 about opening the systems in order to analyze them and propose securing solutions. So in this part of the talk, I will briefly describe the instrumentation journey, so the path that we followed in order to identify the observables, so the hardware interfaces where the radio frequency energy would get coupled and go inside the target, and the software interfaces that can give us information about those hardware phenomena. And the second main challenge was to gain access to the software stack and be able to run our own software. And as we will see, this was not so difficult because, in fact, the target that we chose basically had no hardware security at all. Our target is a civilian quadcopter, so it is composed of an aircraft, a remote controller, and a software application which is intended to run on the pilot's smartphone. The remote controller is the Wi-Fi access point, and there is a Wi-Fi link mostly to bring connectivity between the software application and the aircraft. The software application is a Wi-Fi client, and there is a user interface which gives some information, some telemetry data, and also which allows to send some configuration commands and some high-level commands, such as maybe come back home or land now. There's a 5.8 gigahertz radio link for the real-time remote control commands. And on the aircraft there is also the inertial measurement unit and everything the drone needs to self-stabilize, a GPS receiver to help this stabilization and also to help the drone maybe follow a path, a pre-programmed path. It behaves as a Wi-Fi client, and it has also a 5.8 gigahertz radio interface. So the aircraft is an interesting target because it is full of sensors, and from our point of view in our study, if we can gain access to raw measurements from those sensors, it can be a really interesting way to observe the effects. So we identified the coupling path. So the front door coupling is mainly focused on the hardware interfaces that are meant to collect energy. So basically it's the radio frequency interfaces. And we, as software observables on those interfaces, we hope that we can get the signal quality, some information about the communication rate, to analyze if we can detect some disturbances on those links. On the backdoor coupling path, we identified everything that's inside the box and that is not really intended to collect energy. So basically we would like to get access to the sensor readings, to also some inferred or calculated information. Somehow you can have some redundant information, a raw sensor reading and the same information but calculated from two other sensors reading and so on. So it's interesting to see the discrepancies. We would like to get some information about the motor states, somehow information also about the operating system. So we will try to get a look on the operating system logs and see if we can identify effects on the operating system side. And we're also interested in all the embedded communication links. Maybe we can identify some disruptions on the embedded interfaces from internal SOCs or system on chips. So now I will briefly describe the funny journey that we had on the software instrumentation. So the idea is basically we have to find a way to root. We have to identify on which system on chip we have to get root in order to get the observables that we want, in fact. So we have then to identify how we get access to the data and how we can interpret the data. So what it means. From the raw readings, we have to know how to get the real information. And then the strategy is to design a specific software, a specific piece of software that we can deploy on the UAV in order to gather all the data that we want to monitor during the tests. So the way to root was quite easy. First, there is a documented weakness on the internet on the target we run the test on. So the idea is if you are on the Wi-Fi network, then you can enjoy a root telnet for free. So we first did that, and this gave us access to some information about the operating system. So it was an OpenWRT, which is an embedded Linux dedicated mostly to Wi-Fi routers. We observed the partitions, the file system, and we identified also the running services. So, and the vendor modifications on the genuine OpenWRT. And mostly it was configuring the Wi-Fi in order to connect to the remote controller. And then there was one single piece of vendor software running on the UAV. So we started to play with the target and to modify the startup sequence and so on. And suddenly we lost the Wi-Fi interface after a reboot. So we had to find another way to get our root shell back. So we searched for factory reset on the internet. We didn't really find anything on that topic. And we had a hurry on that work, so we decided to go straight to the point. So we opened the drone and we found the Atheros SOC, and then we found the memories that were involved in the SOC operation. We unsoldered the flash after confirming that it was the right memory, and it's not really surprising, but this memory layout is quite common. And there was a first version of the firmware which is static and which is intended for firmware factory reset, in fact. And my mistake was in the second part here. So the idea was just to recopy the first part on the second part, so we did that. And then we put the flash chip back inside the drone, and we enjoyed again the telnet vulnerability. Back to the start. But then, as we opened the target, we continued to analyze it, and we found it was fully documented on the PCB. You really had all the information you needed on the PCB. There was plenty of markings, plenty of labels, plenty of test points, plenty of UART or URAT interfaces, and also a lot of other interfaces documented. So this was really, again, trivial to analyze this PCB. And the diversity of the interfaces has also an interest for us on the analysis of the effects later. And so we found a UART on the Atheros system on chip, and it exposes a U-boot console first. This is really classic. And then a root shell for free when the OpenWRT finishes starting with a small busy box. And then I did some research, and in fact it was fully documented on the internet. So internet knew about it. I just didn't really know how to get the information from internet. We analyzed the vendor software, which was running on the OpenWRT, and we saw that, among other things, it listens on a serial port, an embedded serial port, and it grabs the packets that it receives on this port, it masks them, and then it sends them over the Wi-Fi interface. So we thought that it might be the information that is displayed on the graphical user interface on the software application. So we say, okay, if I can have telemetry data here, maybe I can use it for monitoring the effects. So, and fortunately, we saw that there was a debug flag for launching the binary that logs all the clear text packets received on that embedded serial port to the syslog. So it was okay for us. We analyzed the serial ports, the other serial ports, and we found out that it mainly interfaces between several system on chips and several sensors around the system on chips, and also communication links between the motor controllers and some system on chips. So there was somehow a data collecting branch and an action branch, a motor controlling branch. Then we analyzed the software, the mobile software application, which received data coming from the OpenWRT SOC. The masked data, it unmasks the data, and then it plots information for the user. So it's the information that we need to understand, and all the information about the frame format and the meaning of the payload and the way to interpret the information, the data that is in the payload. Everything was in the mobile application. So with that information, we just wrote a parser, and we had information about the motor states, the information about the battery temperature, information about the attitude of the aircraft, its position, the GPS data, information about the radio frequency links, link quality, for example, and some raw sensor values from the inertial measurement unit. So what we did for running our tests, we changed the startup script in order to add the flag, in order to put the vendor software in debug mode. And then we run extra scripts in order to also log to syslog, and then we configure syslog to send the logs to a remote server. Our remote server is our monitoring machine, and we are ready to parse the packets, store them, and also plot them in real time in order to have a real-time analysis of our stimulations. So now we're ready for the tests. So we put the target in a Faraday cage. We also put the remote controller, a smartphone with the smartphone application. We put also a Raspberry Pi, which is connected to the Wi-Fi network inside the Faraday cage, in order to gather the information that is coming from the aircraft, from our software, and route it outside the cage through an optical fiber link to our monitoring computer. We have a source, which is a software-defined radio and a bunch of amplifiers. And we are able now to send some stimulations, put the target in a specific electromagnetic environment, and observe the effects gathered from our software. So first, the effects on the front door coupling interfaces. This is exactly what we expect. It's kind of the dummy test that we do in order to see that the setup is okay. This is the received signal power on the aircraft on the Wi-Fi interface. And we see that when we start our source, we immediately see an impact when the carrier frequency of the source is a subharmonic of the 2.5 gigahertz. So this is exactly an expected result. We also observed results on a value that is called vertical speed, which I didn't really found the unit, but I see that I am able to create an activity on the vertical speed. Yeah, I forgot to mention that for the tests in the Faraday cage, in order to make it easy for us, the drone was put on a table and we took the propellers out of the drone, so it's never flying. And during this test campaign, we didn't start the motors. And here we are able to make the drone think that it is going up or down. And then we see in the bottom graph that there is an altitude offset that is inferred from the information from the sensor that gives the vertical speed. And we see that the drone really thinks that it's going up or down. This is an interesting effect if you want to have an instantaneous response and make the drone go up very quickly when it is getting close to your protected zone, for example. We also have been able to observe effects on the battery temperature sensor. So the middle graph is just a zoom on the upper part of the upper graph. And on the bottom you have the temperature of the battery. And what we see is that when our source is on, we are able to generate an offset in the battery. And in that case, the offset is negative. So we are able to lower the sensor reading from several degrees. And we tested that a bit further, and we noticed that there was a linear relationship between the parasitic signal amplitude and the effect amplitude. So we are able to control somehow from how much the offset will be. This can be, I guess, interpreted as a phenomena that has been described 2 years ago here, and in a talk from Alexander Bolchev, I guess it was on ADCs, and on that topic we think that it's an analog sensor, and there is an ADC that is trying to digitize the analog signal, and our parasitic signal frequency is much higher than the operating frequency of the ADC. So this generates this kind of effects, and I think it's an amplitude demodulation of the parasitic signal. We also observed effects on the yaw. So the yaw is the horizontal angle of the head of the drone. It's the head direction of the drone. And we saw that we were able to have two kind of effects on the yaw angle reading. The first is a kind of locking effect. So we have here the unit of the graph is a tenth of degrees. So here we have a 70 degrees shift of the yaw angle reading. And then it gets stuck, and even if we stop our source, the yaw stays at the offset, the obtained offset. And we also observed that we found a sort of a trigger to zero the yaw reading. So when our source gets on, the yaw value gets to 0. So as there is a feedback loop, I guess the drone would counter-react And when it sees that the yaw goes to 0, and it knows that it is supposed to have a yaw of 10 degrees, it will modify its behavior and control the motors to compensate. So again, this can be an effect that could be exploitable for some remote control or a very localized remote control of the drone behavior. We also observed perturbations on the embedded serial buses, so it's interesting because we can somehow isolate some parts of the PCB from the intelligent parts of the PCB, so it's really interesting. And we also saw effects on the remote controller. As a conclusion, I would say that we showed that the methodology that we suggested in order to get information on the effects of intentional electromagnetic interference on electronic systems is working well on a UAV. We noticed that somehow when the devices are proprietary or closed, it might require some agility, despite the fact that here, again, there was no significant security measure on the hardware part of the system, so it was kind of a comfortable study. The telemetry data is really interesting to observe the effects on these kind of targets. And we think that the effects on the sensors can lead to, thanks to this feedback loop, to some flight path control or some flight path disturbance. And this maybe can be used in order to make the drone go suddenly away from the target when it gets close, and then the effect stops and the drone comes back, and maybe you can shift him away again. Even though observing the effects is something interesting and is also already a big challenge, but generating the electromagnetic environment, so creating the source in order to bring the target in the desired electromagnetic environment is another big challenge. So yeah. And we intend to maybe diversify the targets, look also into the forensic sides, so maybe find markers that can give a clue that the drone fell because of the use of a radio frequency directed energy weapon. So it's interesting to get information that can be used in forensic analysis. And what would be funny is to try to combine the effects in order to get this kind of fast response and try to make the target shift a bit, or yeah. The references, of course. Thank you very much.
So we're going to move on to questions. So who wants to start with the first question? No one?
Hi, interesting presentation. I was wondering, is this research based on one type or one model of drones, or did you look at multiple ones, and how did they react, I mean, among the different models or types?
Yes, the diversifying the targets is in the further work section, so this answers the second part of the question. And the main point was just to verify that this technique is suitable for this kind of targets. So we started it with one product, but people that need to really make this assessment on a whole range of products can now derive from our technique, maybe, and run their own tests.
Anyone else?
what you have been showed is about drones that are very cheap for civilian purposes. But for example, if you can put inside very easily a lot of anti-jamming techniques, direct spreading, frequency hopping, MIMO diversity, and so on. So eventually, how you are intend to cope with such hardware, because it's today with the hardware is so cheap, it's very easily to insert.
Yes, thank you for the question. There are 2 key points in your question. The first key point is why to focus on civilian command-off-the-shelf drones, and the main reason is that they are used by law enforcement because they are cheap and they are easy to operate, and they can be destructed, and they can be forgotten on the field easily. So they are getting used now in some critical operations. So it's an interesting target. The second point was about the jamming and the anti-jamming and the protections that you can find on other classes of drones, and even on some civilian command-off-the-shelf drones. The idea of our research was not focusing only on the jamming of the radio frequency communication links. We try to identify and analyze effects on the PCB, on the tracks, on the sensors, and so it goes much further than just the communication interfaces, in fact. But this part can also be somehow hardened, and I hope that the military drones that we could not inspect in our study are somehow hardened again against these kind of attacks. I don't know. Yes, there is a question here.
Thank you. For the measuring part, did you consider recording the RF signal coming from the drone to kind of see that a glitch happened or that something happened?
The radio frequency emanations or
Yes,
the radio
yes,
frequency
yes.
communication?
The communication after doing your glitching or the...
Okay. Only on the communication?
Yes.
Or, okay. No, we didn't really do that. I guess during the test, it's an interesting point. There are several signal types, and sometimes we have a continuous signal, and we are looking for an effect during the presence of the parasitic signal, and somehow we are looking for the effects after the parasitic signal stops. So it's I think some of the effects that we observed occur after we stop our source. Yeah. But we didn't really formalize the assessment of this part of on the radio communication links.
Thank you.
Thank you.
Any more questions? Well, I guess we'll close the talk. Thank you
very
for your
much.
time.
Thank you.